Have you ever wondered how the blood flows in your cardiovascular system? Have you ever thought about how the heart functions and that whole interaction between blood flowing and nutrition and breathing and all those things that are important to us? Well, if you have, this lecture is going to be a beginning step into that semester-long adventure we're going to have toward understanding both the mechanics and the energy, the engineering, and also a little bit of the physiology of this amazing system that is driven by the heart, but that encompasses our whole body, about the cardiovascular system. Now, I'm going to start with a little sideline. Students ask me every year why I wear all these crazy bike socks, and students even like them. So since you don't get to see me in the classroom, you'll get to see some bike socks. I'll try and highlight a pair each lecture, and you can share some of my collection with me, and just maybe to brighten up your day a little bit. So what I want to start with is a very brief recap of what I'm calling last week's episode, where we talked about flow in the context of Darcy's law, and we came up with a fundamental relationship as well as a specific one for how flow can occur in the setting of especially a filter. Darcy's law is really useful to think about in the context of flow through ditches, through any container with water, with a filter in it that has a certain permeability. And that was really useful for the city of Dijon, where Henri Darcy enabled them to get water from the nearby lakes. Not so relevant for our bodies and the cardiovascular system. So today, we're going to make the transition into the context of flow of blood and liquids in general, but mostly with an idea that blood is in our mind. We're trying to understand how things flow in the body. And to do that, we have to slightly modify Darcy's law and describe, first of all, why we need to think about flow, and then some of the engineering and equations that describe flow. So, first part is, what sort of transport systems do living systems have? So you've learned about diffusion, learned a little bit about flow. Is it possible to have an organism that operates just on diffusion? Do we need pipes or a way to move liquids around inside our body? And the answer is, for very small organisms, typically single cell organisms like you see here, that's really all we need. We can have a diffusion-based system inside a living organism, and things will just move through diffusion. Now, from reading your textbook, you know that's pretty slow, right? To diffuse across my height roughly, it takes something like 6 years. If diffusion were what we're using to get a molecule of oxygen from my lungs to my feet, where my foot muscles are. And so it's not a very good system when it scales up. It turns out there's a family of animals, critters, that live, they're bivalve mollusks and others like them, who actually have a hybrid system. This may be a little bit new to you, that has diffusion as a major component, but has the original beginnings, let's say, the origins of a flowing cardiovascular system, as you're more used to it in the context of mammals and other large animals. And so you see in the figure here, there's a heart that does push blood out. But then at the end of the blood vessels, there are just these terminal vessels that let the blood and whatever's in the bloodstream sort of leak then into the tissues, and then diffusion takes over, and then the blood eventually gets captured back into another sinus system that allows it to flow back to the heart and be pumped again. So the blood spends part of its time inside a blood system of vessels, and part of its time diffusing as a liquid. Now, of course, in mammals, you see here, we're a little different. We have this 4-chamber heart that drives things, and the image you see here shows the heart, but more importantly, it shows it in the context of the cardiovascular system, at least schematically. And it describes the two different systems we have, one that provides blood to the lungs for oxygenation and removal of CO2 and other bloodborne gases, let's call them. And then the systemic circulation, where we're exchanging a lot more different nutrients, byproducts of metabolism, all sorts of things, to the tissues. And we'll learn more about that particular system. In fact, we'll model that system as the semester goes on. So I want to focus, really put us in the context of this mammalian system or large animal system, because there we really do depend on a couple of key things. And one of them is flow through vessels. One of them is having a container or a set of containers, pipes that transport the blood around to get them to the tissues where the tissue exchange happens. And this is a little bit like a delivery system for trucks. I mean, you load up with cargo at one end, you pick up your favorite device at a store somewhere or at a warehouse somewhere, and then it gets driven around or flown around the country and then gets brought to you at home via delivery truck or to a store where you go pick it up. And while all you really care about is picking it up and maybe paying for it, there's a whole system in place in the background that you hopefully don't have to worry too much about. Hopefully it works and you get the shipment quickly and you find the product you want in the form and color you want it. And the body's a little bit like that. There's a whole cardiovascular system in the background that's worrying about this whole delivery. And then the actual exchange, the picking up of the goods, that's what happens only in the capillaries, which are these tiny, tiny, tiny vessels that have a lot of exchange, a lot of diffusion. So diffusion still is important in our bodies, but it takes place only in the context of these capillary vessels that have very thin walls and that allow whatever's needed to go in whatever direction is useful back and forth between the blood and the nearby tissues. And that's how our system works in a nutshell. Now, for today, I want to focus on the delivery system. This is like the highway system or the flow system that makes this all possible. And we call this hemodynamics, hemo because blood's involved. And it's dynamical because the heart beats and there's flow changes over time. We're going to treat the system a little bit sort of artificially staticky, just to simplify things for the moment. We'll get to dynamics soon enough. And as usual, I'm sort of fascinated with some of the history and some of the characters that brought us all this knowledge, made these insights. And it turns out that there were actually two people, a Frenchman and a German, who never really collaborated as far as I can tell, but certainly were aware of each other's discoveries and thoughts. And so the full name of this Poiseuille's law that you'll be hearing about really should be shared between the two of them. So and maybe this is a typical case where Jean Poiseuille was the physiologist and the physicist, and he was French, and this was also during the same time as Henri Dassy, this early part of the 1800s or 19th century. And he also knew about a colleague, a German engineer, a civil and hydraulic engineer, and his name was Gottlieb Hagen. So Hagen was, again, an engineer. And so the two of them were aware of each other, complemented each other in terms of their skill sets, and both had an amazing impact on education, their various fields. But one of the discoveries that came out of that was this law that you've certainly read about in the textbook called Poiseuille's law, or actually Hagen-Poiseuille's law. So what I want to do now is not just go through the same material that's in the textbook, because you've seen that before, but to take you through a process that I hope you can use generally when you think about how you want to characterize and quantify a behavior, because this is another example that fits into the previous case where there's a driver and there's an enabler and then there's a flux, and there's a relationship between the various parameters that determine that flux. And you can really, with some geometric considerations and this basic notion you saw in the last lecture, you can already come up with a lot of the essential elements of this expression, this equation. You don't really have to memorize, at least not all of it. So let's start with the driver. It's always the essential part of this process. And as we saw before, this is a flow situation, so it's not too surprising that we have to think about a driver in terms of a difference in pressure between two ends of a pipe, let's say, or that section of a pipe that we're examining, that we're trying to quantify the flow through. And so that pressure difference is our driver. It's quite simple, right? Just like with Darcy's law. Now, similar to Darcy's law, you can imagine, okay, what were the factors that will make flow either easier or harder? And it doesn't take much to walk through them, really, when you think about it. Cross-sectional area is going to be a key one. Obviously, the bigger the pipe, the easier it is for flow to occur. So the more flow, all other things being held equal, the more the cross-sectional area, the easier the flow, the larger the flow. And that's going to allow us to write down an expression and say that flow is in some way dependent on cross-sectional area, directly proportional. In fact, we're going to assume to cross-sectional area. And we can write down the expression for area. It's pi r squared or pi a squared. We're using a for radius here. And we can write down this simple expression to say that the flow is a function of area, which is equal to pi a squared. Similarly, as with Darcy's law, we can imagine that the longer that pipe is, the more it's going to impede the flow. So as the pipe gets longer, there's just, anything that slows flow down, that reduces the amount of flow, is just going to get worse and worse. So the longer a pipe is, the less flow rate we're going to be able to achieve through that pipe. And that's, we're calling L. And that's going to have an inverse proportional relationship. So we're going to remember that when we put the equation together. So we can write it here as this proportionality of Q is proportional to 1 over L, the length of the tube. And then there's another factor we didn't talk about last time, probably should have, but it seems to fit even better here, is this thing called viscosity. So this is like the thickness of the liquid. And it's easy, again, to imagine just intuitively that liquids that are viscous, and what would be a viscous liquid? Well, let's think about, I don't know, an oil is more viscous than a water. Extreme example, honey, some very thick substance that clearly flows only with difficulty. So that's a highly viscous substance. And of course, there's a definition for viscosity, and we'll get to that later. But the main idea here is sort of an intuitive one. And then, so you can think about, okay, what effect could viscosity have on flow? And I don't think it's hard to imagine that the more viscous, the slower or the less flux or the harder it is to have a flow rate. So whatever way you want to look at it, the flow will decrease as viscosity increases. And that's another inverse relationship. So we can write down this other proportionality that says that the flow rate is proportional to the inverse of viscosity. Now, that already gives us a lot of information. We can put all this information in a box and say, okay, how do we combine all that mathematically to come up with a guesstimate, or at least hopefully an approximation of how flow relates to these various quantities, the relevant quantities that describe a situation that we would have in the body. So we would definitely write down that the driver being the pressure difference, we'd write that in the numerator. We'd say, well, area, the pi a squared, that's also in the numerator, that's a direct proportionality, so we'll leave it in the numerator in this equation. And then the other two factors, the length and viscosity, we'd put them in the denominator because they're inversely proportional. And so you could write down an expression like the one you see in front of you and kind of think, well, that's at least proportional to the factors that I know that I can measure, that I can imagine capturing. But the question is it correct? And this is another step. You can get part of the way there just using this kind of logic, but it turns out when you get quantitative, there are other factors that come in. And some of those factors come in through measurement. So what we do in science a lot is we hypothesize a relationship like this. We say, well, if we're going to test this relationship, then we have to set up an experiment. We have to measure flow like you're going to do in the lab. We're going to measure flow as a function of these different parameters and see if it all depends the way we have it figured out here. And if we can ideally vary those parameters, then we can see the relationship specifically to those parameters. So we might vary the pressure, or the pressure difference, because that's really the factor here, is the difference between the input and the output pressures. We might vary that pressure difference and see what the resulting flux is. We might vary the cross-sectional area and see what the change in the resulting flux would be. And eventually we can test this equation, this idea, with data, and then determine whether or not it's correct. And then maybe adjust our formula based on the data and the results of that comparison between the formula and the data. And that's very common practice in science. This is how we do at least a reasonable number of experiments, especially in the area of engineering, where we're oftentimes trying to quantify things. So this is what can lead to the realization that unfortunately our equation is wrong. It's kind of a bummer, right? So our equation won't work out with the data we would measure. And so, and of course you know that because you've seen in the textbook what the actual equation is, which you see there. And if you look at that equation carefully, you say, well, what's different about it? Well, it's not a squared, it's not just area, it's a to the fourth. That's a pretty big factor. That's a pretty big difference, taking something from the second power to the fourth power. And then there's an 8, a factor 8 in there. And that's not uncommon when we quantify things that somehow due to geometry, maybe there's another, there's a, we oftentimes put a constant k and we determine that k from measurements. But in this case, we can actually derive, the origins of both those numbers. And I'm going to focus not so much on the 8, which is a small thing in the global scheme of things in terms of determining accuracy of equation, but to focus on that a to the fourth, because that's kind of a big factor. It's going to have a large influence on the results we get from our equation. And why is that? Well, to understand where that comes from, we have to think a little more about how blood or liquids in general flow through pipes. And just think about how that all plays out. And this is kind of interesting engineering because it has to do with the fact that at the boundaries of a pipe, we have a layer of fluid that's moving very slowly, maybe not even moving at all. Maybe it's just sort of stuck on the edge of the pipe. Whereas in the middle, we have a region of tissue that's flowing, a region of liquid, that's flowing quite strongly. So we don't have consistent speed of the flow across the cross-section of the pipe. And that changes things. Then we don't have a simple dependence on the cross-sectional area. Instead, we don't have a line of flow all at the same velocity. Instead, we have a distribution of velocities across that pipe. So when we have this distribution of flow rates across the pipe, as you see there, we can actually measure that too. We can put little flow meters or watch colored particles go by. There's different ways to measure this. And we will determine that the profile of that velocity, of that rate of flow of the liquid in the pipe like this, will have a parabolic shape. So instead of a flat wave moving at constant velocity, we will have a bent shape in which the middle portions are moving much more quickly than the portions of liquid at the edges. And you say, how do you picture that? How does that work? Well, you picture it as layers of liquid that are flowing at different rates and sort of sliding by each other. So the center has you can picture this in 3 dimensions as sort of a core at a certain velocity. And the next out, you have a concentric cylinder flowing at a slightly slower velocity, and out it goes. And so you have these layers of liquid, each flowing at different rates. Now, not surprisingly, the word for layer is lamina, and this is called laminar flow, which is something you may have heard about, in contrast to turbulent flow, which we'll talk about some other time. So we have laminar flow, and under those laminar flow conditions, we have different velocities at different regions within the pipe, and that leads to this parabolic profile. And parabolic, that's a quadratic function. You can kind of wave your hands a little bit and say, well, it's a parabolic function. Area is a quadratic function. Put the two together, we're going to get a fourth order function. And for our purposes, that's about as much as we need to know. Now, of course, there's a more mathematical derivation that will get you the same result, and that's, of course, what Hagen especially is responsible for, figuring out what this relationship is in a quantitative way. And that gives us the formula we can work with, this Poiseuille's law, that we can use to make at least approximations about the flow rates using this expression that you've learned in the textbook. Now, it's important to draw your attention once again to the basic formulation that we have here, which is just like Darcy's law and like a lot of others that are going to come, and that's that we have a flux, Q in this case on one side, and on the other side we have a driver, the change in pressure, the relative difference in pressure across the segment of vessel we're concerned with, in this case divided by resistance. So we're going to see this again and again. This, of course, is Ohm's law in electrical terms. You may recognize it already. But we're going to see this again and again where we have a flux or a flow as a function of a driver divided by resistance, or a driver multiplied by an enabler. So the enabler is the inverse of the resistance. And we'll see that again and again. In fact, we even have terms for this, specific terms for this that we'll see today and use again, because if you write the equation this way as Q equals delta P over R, we see that resistance is in the denominator of the right-hand term. But we can call this enabler, in this case, a conductance. We can say it's the inverse of resistance, and it's hemodynamic conductance. Not a word that's used that often. We usually talk and write in terms of resistances, but we have this notion of conductance. This allows the flow. It's like the permeability across a membrane of the filters that Darcy's law described. So it's really the enabling term of this equation. And so we have the same situation again as we had before and as we will have again. Now another thing that we're going to have now explicitly for the first time is something that also belongs to every equation. Every time we write down an equation, and we have to be concerned about this as engineers, is we have conditions under which that equation holds, or assumptions that are built into that equation. These assumptions show up in the math when you derive an equation carefully with mathematics. They also show up in the kind of assumptions that went into this discussion we just had about what determines flow. For example, we assumed we had laminar flow. That's an assumption. There's a thing, as you know, called turbulent flow that's non-laminar, and that's going to change things. So the relationships that we have described by Poisson's law will hold under the condition of laminar flow. It's one of the working assumptions, one of the constraints. Another one that again would only show up in the mathematical derivation, another one that shows up is that the length of the pipes we're dealing with have to be fairly long compared to their cross-sectional area. So if we had short, very wide pipes, which we don't typically have in the body very much, then in those conditions that equation would break down. It wouldn't be as simple as the form that you've seen in front of you. This equation also assumes that we have a fluid with a constant viscosity, a constant thickness to flow. And that again is an assumption we have to question. Turns out that blood is not a very constant viscous solution. What does constant viscous mean? It means that the viscosity or the thickness, and in this diagram you see the actual definition of viscosity as this ratio of the shear stress that you apply to move liquid and a function of the shear rate, which is the rate of deflection of that liquid when you apply the force. And again, these are more details than we need for this discussion. But there is a definition, and you should know that. This viscosity changes as a function of the actual flow rate. So as we get more flux, as blood flows more rapidly or more slowly, the viscosity is not a constant, it actually changes as well. Now, that's a little bit mind-boggling, but we can explain that later. At this point, we just have to work on the assumption that as long as we have a constantly viscous fluid, which we also call a Newtonian fluid, as long as our fluid is Newtonian, then we meet that condition of Poisson's law. And then the fourth condition, the one that we will add to in next week's lectures, is this notion that we have rigid walls. Rigid wall means you have like a PVC pipe or a metal pipe. And it doesn't take much imagination to picture that the vessels in our body is not quite PVC. They have a lot of distensibility, they're elastic. When the pressure goes up, they stretch and they get bigger. And that's an important characteristic that we will spend a lot of time talking about. But these four conditions, it turns out when you do the derivation really carefully instead of the way we did it, if you do it really carefully with all the math and the physics behind it, these four assumptions have to be met in order for that equation to be accurate. Now you could say, what's the use of equation that has all this baggage attached to it, that all these assumptions and constraints, how good is that and how useful is that? Well, it turns out all equations actually are inaccurate at some point. There is no equation that perfectly describes anything. I think it's pretty safe to say that. Another extension of that is that no computer model is perfectly accurate. But some are useful and some equations are useful, and they're useful sometimes in a quantitative sense, and sometimes they're only really useful in a qualitative sense, that they allow us to predict behavior that may not be quantitatively perfect, but allows us to recognize relationships between, let's say, the radius of a vessel and the relative flow of blood through that vessel. These are important tools, and we engineers like equations as tools. They're important tools to help us, give us a sense of how a system functions. So even when an equation isn't perfectly accurate, it still can be very useful, and we'll try and show you some examples that at least, may sound like they're kind of useful in this course, in the homework assignments. But again, this is something we will see again and again, that equations are always approximations. We just have to get used to that. Now, I've talked about pressure differences. I've talked about resistance or conductance, hemodynamic resistance, hemodynamic conductance. This is now starting to become a new jargon that we have to become comfortable with and that we will expand, because there are a number of well-defined hemodynamic parameters that we're going to have to get a handle on. We're going to have to understand what they mean, what the units are, in order to solve problems and in order to communicate with other engineers, with physicians. So flow is one of them. Flow rate, that's always a volume per unit time. There are some other variations, but generally we're talking about volumes per unit time. And then we'll have resistance, which is this ratio of a pressure to a flow. And it will have, understandably, some really odd units. You see those in the chapter, and we'll have to get comfortable with those units, because there are SI units for this. It depends on the pressure units, of course, that you're using. But it will have some weird units, and we just have to keep track of them. Shouldn't let that distract us. But it is that ratio. You'll see when it comes to electricity, of course, you'll recognize that, well, it's voltage over current, and that gives us ohms. So we have nice simple units for that. They're not quite as pretty in hemodynamics, but they're the same idea. And then finally will come next week, that's the hook to keep you anticipating, we'll talk more about compliance, which is this factor that determines how vessels distend when pressure changes. So why, when our pressure goes up, our vessels will actually grow, and what effect that growth will have on the flow rates and the dynamics even of flow that we'll start to get into next week. So that should hopefully fill in a few of the gaps around the chapter. Hope it was useful, and hope you enjoyed the socks and the t-shirt, and we'll see you soon. Thanks so much for your attention.